Okay, let's look at this problem. This is a linear algebra problem. It said that the system of linear equations given, find the reduced echelon form for the augmented matrix. Is the system is consistent? If yes, write down the solution set in parametric vector form. Okay. The augmented matrix we have here, it's a 1, right? 2, 4, 3, 4, 0, 1, 2, 1, 2, and 2, 1, 2, 6, negative 1, right? What we can do is we can let row 3 minus row 1 times 2, right? So that should give us, it's still 1, 2, 4, 3, 4, 0, 1, 2, 1, 2. This is it's going to be 0, right? Negative 3, negative 6, 0, and excuse me, we have negative here. Okay, so yeah, that should be the work. And then right now, you see we find a pivot. Now we're gonna trying to use the next pivot to reduce. So as you can see, we can use row 3 plus row 2 times 3, right? So that will give us, so it's a 1, 2, 4, 3, 4, 0, 1, 2, 1, 2, and then we'll have 0. So this part is going to be coming to 0, right? And see, this part will also 2 times 3 is 6, so this part will also give us a 0. And row 3 plus 4, row 2 times 3, so this is going to be coming to 3. And this part, negative 9 plus 6 give us is negative 3, okay? Alright. So we can do one more thing. We can just divide it 3, row 3 over 3. We're going to have it so 1, 2, 4, 3, 4, 0, 1, 2, 1, 2, 0, 0, 0, 1, negative 1, right? Okay. And as you can see, from here we already figured out is okay, we have 3 pivot position, right? 1, 2, 3, and we have 4 variables. So we're gonna have first of all, we can see that it's gonna be consistent. So let's continue to do the reduced echelon form, which right now we can use row 1 minus row 3 times 3, right? That will give us is 1, 2, 4, 0, and then this is minus 3. Subtract it, it's going to be coming to a 7, okay? Meanwhile, we're going to use the row 2 to subtract row 3. Okay, so it's going to be 0, 1, 2, 0. This part minus this is going to give us a 3. And then so I still have 0, 0, 0, 1, negative 1. Okay? And what we can do is we can use row 1 to minus row 2 times 2, so that we can get rid of this 2 here. So it's going to be 1, right? 0. So 4 minus 2 times 2 is also give us 0. Okay, so it's good. This is 2 there, and this is going to give us is a 1. We're going to have a 0, 1, 2, right? 0, 3. And we're going to have 0, 0, 0, 1, negative 1. So up to here, and you can see we down. Why? Because you know, the 3 pivot position here, you know, for the pivot position, this is the only value, the other is all 0. Same for this part. And we can see that the x3 is free, right? X3 is free. So we can write down that is x1 equals 1, x2 plus 2x3 equals 3, and then x4 equals negative 1. Okay, that's negative 1. So we can solve x2 in terms of x3. So x2 equals 3 minus 2 times 3x3. So if we write it over, so part A is down. Part B, is this system is consistent? Yes. And how do we write down into the parametric vector form? Well, as you can see, x1 is 1, right? x2 we can write as 3 minus 2x3. x3 is here. x4 is negative 1. Okay. So in this problem, what we can write is, we can write this as 1, 3, 0, negative 1, plus x3 times 0, negative 2, 1, and 0. Okay, so you know, this is again, this is what we can see, that the parametric vector form. So if we denote this is vector u plus x3 times vector b. Okay, so that's how do we do for this one. Cool. Problem 2, it's determine the values of h such that this matrix, this is an augmented matrix, is a consistent linear systems. Okay. Okay. So right now, as you can see that this augmented matrix, if we're starting to do the row reduction, 1, h, negative 5, 2, 8, 6 here. If we use row 2, subtract the 2 times row 1, what we can have is 1, h, negative 5, right? This is becomes 0. This is going to becomes into 8 minus 2h. This part becomes into 16, right? Okay. So if, remember, this part, and the thing is, if this system, linear system, is consistent, do you realize that that means we cannot have that? So if system is consistent, so you cannot have like a 0, 0, 0, da 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 b happens, right? I mean, of course, b cannot be 0 happens in the last row. Otherwise, that will make our system inconsistent, because, in other words, you're going to lead to an equation to 0 equals some row number, which is not true. So to avoid that happiness, do you see that as long as we need to make sure that 8 minus 2h does not equal to 0, that is h does not equal to 4, we should be good enough, right? We should be good enough. In other words, only situation is when h equals 4 will make my system inconsistent. And then as long as h is not equal to 4, we're good to go. Okay. Alright, problem 3. Give 4 vectors v1, v2, v3, and v4. Determine if v3 is in span of this. The terminology span means it's a set of all the linear combinations c1, v1 plus c2, v2, right? So, in other words, to determine if this is in the span, it's equivalent to see that, okay, if I can write my x3, my v3 into a vector equation like this, it's a linear combination of vector v1 and v2. More, we can dive in this. Do you realize that the problem becomes into, okay, help me to find if this well, it says x1 minus 2x2 equals 1, and then, well, 0 equals 4, 3x1 minus 6x2 equals 2. So the problem becomes into, okay, so this is the vector equation, this is the system of linear equation. So the question of if v3 is in span of this is equivalent to answer if this system of equations consistent or not, right? So after here, you see, we're good to go. Why? Because immediately we can claim that this system of equation is inconsistent. Why? Because you have the 0 equals 4, so it's not consistent, and hence, so the vector v3 is not in the span of v1, v2. Okay. So yeah. Part B, it's if v4 is in span of 1, v2, 3. Well, if we recall what our v4 is, 1, 4, 2, right? So basically, this is what we want. So it's 103, -2, 0, 6. And then 1, 4, 2, 1, 2, 3. Basically, we're looking at if this is augmented matrix, if the corresponding system of linear equation is consistent or not. Okay, so same thing. Well, as you can see here, we can try to do some row reduction here. And first of all, one thing we can do is, you see 1, -2, 1, 1. And I can swipe row 2 and row 3. So 3, 6, 2, 3 into 0, 0, 4, 2, right? So let 2 and 3 swap, and then I let row 2 minus row 3 times row 1 times 3, so that will give us is 1, -2, 1, 1, right? So 0. So 6 minus -6, that will give us is 12, right? 2 minus 3 is -1. 3 minus 3 gives us is 0. Okay, so we have 0, 0, 4, 2, right? And of course you can continue to do that, to do the row reduction here. So what we can do here is, as you can see, we can let our row 2 divided 12 goes to row 2. We can let our row 3 divided by 4 become our new row 3. So that is 1, negative 2, 1, 1, 0, 1, right? Negative 1 over 12, 0, 0, 0, 1, 1 over 2, right? And, you know, we can starting to do the reduced form. So let row 1 to minus row 3, right? Let row 2 to plus row 3 times 12 over 1. 1 over 12, my bad. So we're going to have negative 2, negative 1, 1, negative 2, 0, and minus row 3 is 1 over 2. We have 0, 1. This one times plus this one is going to be 0. And 0 plus this part is 1 over 24. So we're going to have 0, 0, 1, half. Of course, you can continue, but the result should be very obvious, right? So this system definitely is consistent. You know, so row 2 times 2 plus row 1 is going to give you 1, 0, 0. So it's 1 over 2 plus 1 over 12. That will give us 7 over 12. 0, 1, 0, 1 over 24, 0, 0, 1. So yeah, so this is the reduced echelon form, and we're good to go, right? And so of course, then if width4 is expand, yes, the answer is yes. Okay. And last one, given this, you know, this matrix. Observe that the first column minus 3 times the second column equal the third column. In other words, if we let this is stand for V1, this is V2, this is V3. Notice that what we have here is V1 minus 3 times V2, right? And then equals V3. In other words, V1 minus 3V2 minus V3, do you see is equals to the 0 vector, right? I'm looking for a non-trivial solution for this part. So do you see the answer? It's already here, right? So which is the coefficient of this, right? Because you know, it's just a 1, negative 3, negative 1. So yeah, that's 4 examples, and I'll stop here. Thanks.